the second chapter, looking at hydrothermal precipitates associated with venting on the seafloor, we're going to look at some hydrothermal carbonates where the processes of serpentinization and the venting of those fluids onto the deep seafloor has precipitated carbonates, not in the anhydrite sulfide associations we saw in the previous chapter when we were looking at white and black smoker systems. Instead, we're looking at vent systems where we have a combination of carbonates and brucites, magnesium hydroxide, forming chimneys in the vent zones where these exothermic serpentinization reactions have generated hydrothermal waters which are escaping onto the seafloor and mixing with oxygenated magnesium and carbon dioxide rich seawater. The type area for this process is located near the summit of the Atlantis Massif. It's about 15 kilometres west of the active mid-oceanic spreading ridges at about 30 degrees north and north of the Atlantis fracture zone. This massif is an impressive structure. It rises nearly 4,000 metres above the seafloor to a depth of 800 metres below sea level over a horizontal distance of 20 kilometres, so it's quite a large uplift-related structure. Now, the seafloor in this area was not formed via volcanic eruption, so it's not the basaltic seafloor we've been looking at in the mid-oceanic ridges where we're seeing abundant hydrothermal anhydrite. Rather, it's a zone where we've had thrusting and extreme crustal extension along with long-lived faulting and uplift, and so we've eroded and stripped off that shallow crustal volcanic material, and we're looking deeper into the mantle. And we're looking at what are basically serpentinites, these magnesium-rich rocks which were once deep below that active area of basaltic formation. This particular set of structures, known as the Lost City hydrothermal field, is one of the largest known modern hydrothermal venting sites in the world, and there are a number of venting structures occurring there, of which the Poseidon structure is the largest. So here we can see these rather impressive carbonate features forming, in this case this is the Poseidon structure, a extensive carbonate hydrothermal field at a depth of somewhere between 700 and 800 metres below the sea surface. And this, the largest known hydrothermal venting system anywhere in the world, is capturing something like 30,000 years of hydrothermal activity. The Poseidon structure is the world's largest known single hydrothermal vent structure. Now the fluids here are much cooler venting. We can see the shimmering warm fluids escaping here onto these moderately deep seafloor depths. Those fluids only have temperatures around 50 degrees centigrade. They're quite buoyant. They're flowing out of the walls of the Poseidon structure, and they're often trapped under the concave roofs of flanges in this structure. And we see in the resulting reflective pools what are in effect upside down waterfalls. So here's a cross-section showing you the geology, and as you can see it sits atop a detachment shear zone where mantle sediments have been eroded up to the seafloor surface, and in the vicinity of that fault we are seeing significant hydrothermal carbonates accumulating. This is the detail on the Lost City hydrothermal field, which is in effect an off-axis hydrothermal system. And unlike the previous chapter dealing with hydrothermal anhydrite forming within what were newly formed seafloor basalts, here we're looking at erosionally exposed serpentinized ultramafic and metagrabroic rocks. And we are looking at the discharges of fluids associated with the serpentinization process as it moves through what are relatively high permeability fault and fracture damage zones. So here we have high pH fluids from the serpentinization reaction venting through chimneys, and as they vent, they are precipitating a combination of aragonite, which is the first carbonate precipitate as it interacts with seawater, and then within the structure we tend to see calcite and brucite. Brucite being the mineral form of magnesium hydroxide. They're all forming via interactions with seawater. And so our vent fluid geochemistry here and the formation of brucite along with aragonite is indicating a quantitative removal of magnesium, and we're getting a series of water rock reactions consistent with convective heating at depth between 250 to 300 degrees centigrade, and then convective cooling, so the venting fluids that are precipitating this aragonite, calcite and brucite is forming from venting solutions that are much cooler with temperatures between 24 and 91 degrees centigrade. The aragonite is saturated because this vent fluid is interacting with seafloor as it's escaping as a high pH, calcium-rich fluid mixing with the calcium in the bicarbonate-rich seawater. So we especially see this interaction taking place on the vent exteriors, whereas internally within the vent we tend to see calcite and brucite. If we go to older inactive portions in the breccias, we tend to see vent structures which are calcite-rich. They're lithified, they're brucite-4, and that's because the aragonite has converted to calcite over time. Remember that aragonite is a metastable mineral, and the brucite is soluble, so it's dissolved when it's been exposed long-term to colder seawater. So these are not structures which contain anhydrite. These are structures dominated by a relatively simple carbonate assemblage of calcite, aragonite, and magnesium hydroxide, brucite. The venting fluids are derived by the process of underlying serpentinization, which is converting olivine and pyroxene to serpentinite. Now that reaction, indicated in the blue box, is a strongly exothermal reaction with something like 35 kilojoules being developed per mole of water. This exothermic reaction, this serpentinization reaction, is believed to generate the thermal regime, the heat source if you like, for that venting hydrothermal derived water at Lost City. This is not on-axis deep fluid circulation, it's off-axis hydrothermal activity. This serpentinization process is happening at abyssal settings at great depth, where we have olivine and calcium-poor pyroxene in the mantle, that is precipitates, being converted into serpentinite minerals with the uptake of the hydroxyl groups coming from seawater. This process is also associated with what are 3.5 weight% of other dissolved salts. And so the question is, where are these other salts? We don't see them in these venting systems at Lost City. But some authors have made an argument that the serpentinization process, where we have 3.5 weight% of dissolved salts in seawater, the sodium and the chlorine, may be a source of what I'd call non-evaporite salts, but with the mineralogies of halite and anhydrite at depth, well below this carbonate-dominated zone that we see in Lost City. So the Lost City hydrothermal field is probably driven from the heat source coming from serpentinization, not coming from convective fluids on an active mid-oceanic ridge. Its vents are quite unlike the black smokers and the white smokers we were looking at in the previous chapter. These are much cooler fluids. They're also highly alkaline, and what's interesting is that unlike the fluids that we see in the mid-oceanic ridges, these venting serpentinization fluids are high in magnesium and low in hydrogen sulfide. Very different in terms of their chemistry to what's happening on a mid-oceanic ridge. But these vents that they build are huge, up to 60 meters, 200 feet in height, and they're composed purely of carbonate minerals, not anhydrite nor sulfides. In terms of their chemosynthetic microbial communities, it's quite diverse and quite rich, but these fluids that are coming out of these systems are also quite methane rich. So what we tend to see is a different biotal assemblage, a chemosynthetic assemblage, which is quite distinct from the assemblage we see with the tube worms on the mid-oceanic ridges. So the vents themselves are not composed of serpentinite. They're hosted and they sit atop a serpentinized succession. One of the common associations we see here is with sepiolitic clays. These are magnesium silicate hydroxyl hydrated clays. These clays likely formed through the weathering of the serpentinites, and there's an ongoing debate whether the serpentinization process can account for the heat flux from the Lost City field, or if there is an additional magmatic input. Some have also argued, for example, Scribano and others in 2017, that this serpentinization process and the associated hydrothermal circulation may at depth generate significant volumes of what they call rift evaporites, but they're not. They are non-solar salts, so they are not true evaporites, but they are assemblages with possibly the same mineralogy of evaporites. This process, as we'll discuss in the next chapter, pseudocritical precipitation, has never been documented with respect to significant volumes of evaporite mineral phases. We tend to see methane coming off this system as we convert the olivine via methanogenesis to serpentine along with some magnetite. We get significant volumes of hydrogen coming out of these systems. When we have mineral catalyst present, a proportion of the hydrogen generated reacts abiogenically to form methane and short-chain hydrocarbons. So here we have the formation of hydrocarbons abiogenically. Some have argued that this is perhaps how life was first derived back in the Archean, in venting systems associated with serpentinization. There are significant differences in the fluid chemistries at Lost City compared to the black smoker system. At Lost City, we have pHs in the fluids of 9 to 11. We have trace CO2 and trace metals, the opposite of what we were seeing in mid-oceanic ridges, where we tend to have fluids with pHs of less than 2 to 5. They have very high CO2 contents, and they also have, at high temperature, high metalliferous content. This difference in the fluid vents and their chemistry has had quite significant effects on the microbiological community, the chemosynthetic community, where the organisms at Lost City have developed mechanisms that don't involve chemosynthetic processes necessarily based on CO2. Rather, they're processes associated with archaea, which are metabolizing the methane and hydrogen-rich vent fluids, and with cooler seawater, giving us a much more diverse environmental set of conditions. We have much lower temperature fluids, 100 to 110 degrees, versus the 300 degree plus we saw in the hydrothermal anhydrite smoker associations. pHs are much higher, these are alkaline, whereas we had acid situations with fluids with pH of 2 to 5 on the mid-oceanic ridge systems. We have trace CO2 rather than the high CO2 we see in the basaltic ridges and mid-oceanic systems, and we don't see the high levels of metals at the high temperatures of the ridge smoker systems. This difference in the fluid style has had a profound effect on the microbiological communities that are living in these carbonate precipitating vent systems in Poseidon. The organisms here develop a metabolism not involving the chemosynthetic processes based on CO2. Rather, these active biogenic structures that we see, the mats, are archaeal-associated mats, which are living in these buoyantly rising mixtures of warm, methane and hydrogen-rich vent fluids and interacting with seawater at much cooler temperatures. Here we can see that typical interaction where you can see the scalenohedral carbonate teeth-like structures of the crystals along with brucite. This is the triangular platy material, the much larger crystals. And we can also see these gauzy microbial biofilms covering that precipitative surface of the active venting carbonate structures at Lost City. So when we look at the biological association at Lost City, we're seeing a methanogenic biota. Here we can see a typical microbial mat dominated by the methanogens, the archaea, within the cooler vent interiors. And also on the outsides of active chimneys, we get these filamentous strands of bacteria and archaea that are thriving in these zones of high pH, methane and hydrogen-rich hydrothermal fluids. This is sometimes called the microbial fur, and it's this mixing interface where the aragonite and the brucite accumulate. So the first minerals to precipitate are aragonite and brucite. Brucite tends to be more in the interior, but it can also form on the surface. We can also see that the interstices in these carbonate precipitating areas are covered and shrouded by these filamentous microbes, which are forming as a microhabitat for a macrofauna of small gastropods, polychaetes and amphipods. We do see biology forming as chemosynthetic communities, but visually they're not as impressive as the riftia, the annelid shrimp associations that we see on the mid-oceanic smoker ridges. This enrichment of hydrogen with lesser methane and a relative enrichment of the short-chain hydrocarbons is characteristic of the fluid chemistries formed at serpentinization zones at depth and wherever we have seawater coming in contact with olivine and we're oxidizing the iron. Significantly, in terms of the origin of life, the chemical and isotopical analysis of these hydrothermal fluids at Lost City give us evidence that we are forming low molecular weight hydrocarbons abiogenically during water-rock reactions on the underlying basement rocks, where we have these hydrothermal carbonates precipitating. Of course, this leads back, and we'll discuss this in the next module, to extraterrestrial possibilities of life forming from such methanogenic communities in the icy moons of Jupiter and Saturn. So where else in the world do we see these venting hydrothermal carbonates forming? Well, there are smaller scale fields that have been identified with similar biologies and mineralogies as aragonite-brucite associations. These have been found in the Mariana Forearc and the Trench, and they've also been found at Prony Bay in New Caledonia. Now, Prony Bay is interesting because it's forming in the photic zone, where we have a mixing also with meteoric fluids that are being recharged into the Prony Bay hydrothermal field in what is an outcropping serpentinized ophiolite outcrop in New Caledonia. Whereas in the Shinkai Seep in the Mariana Forearc, which is also similar to the Lost City hydrothermal sites, we are seeing a feed at much greater depths where we have these serpentinized derived brines coming up to the surface. So there's New Caledonia, where we have Prony Bay. The white square there is indicating the position of Prony Bay. Here it is a little bit closer up, where we can see that it's quite shallow. It's on the margin of the New Caledonian land area. And we can see that it's associated with what is an extensive area of outcropping, shown in green, serpentinized peridotes, and also some serpentinized dunites. The hydrothermal sites, they're both onshore, but most impressively, they are offshore. And I'm going to show you a video of some of these offshore sites in the positions indicated by the black circles in Prony Bay. Remember that this is serpentinization fluids. We have these extensive ophiolites outcropping on the New Caledonia surface. Here are the venting systems. As I said, it's in the photic zone. You can see it's lit. The morphologies of the venting structures are quite similar. They form as warm hydrothermal fluids arising from the venting positions. Cooler fluids, less than 100 degrees centigrade than we see in the mid-oceanic ridges, but forming what are quite impressive pillar structures in the photic zone in Prony Bay. Here we can see the methane and the hydrogen escaping, and these are rather impressive structures. This is rather interesting. On the left we have a venting structure. On the right you can see the corals forming, and here we have some vents forming on the lagoon floor in zones where we get combinations of photic life and the inorganic precipitates of the venting structures, as we see here, with the methanogenic mats occurring in venting zones, but also in the broader scale we see life forming in the surrounds away from the higher temperature venting zones in that structure. Very rich in hydrogen and methane outflows at these venting positions. This is significant because we are looking at a system where we are seeing what is a meteoric system interacting with these venting structures in this association. And we'll look at this in more detail in the next module, where we look at a succession of cryogenic structures. These structures have implications for life, where the chemistries can be quite similar to what we see as seafloor venting chemistries on moons such as Enceladus, which is a moon in Saturn, where we know we have the possibility of methane generation, and we see how chemosynthesis has also generated short-chain hydrocarbons, which is the basis for life. So it enhances the possibility of extraterrestrial life in some of these icy examples that we'll look at in the next module. And it's because these serpentinization reactions provide both carbon and energy sources for chemoautotrophy, and this is likely to be a possible explanation of the generation of early life. This is a section just showing you through the underlying salty ocean, the ice cap on Europa, a moon of Jupiter, and then those venting geysers on the surface. Lastly, let's compare the difference between the black smoke fields, where we see the ephemeral anhydrite, and the more permanent carbonate serpentinite evidence that we see in these hydrothermal carbonates in zones where we have serpentinization dominating. So let's compare characteristics of the fluids and the vents in the black smoker mid-oceanic ridge association, where we see ephemeral anhydrite forming, as we discussed in the previous chapter, versus the hydrothermal carbonate venting systems associated with serpentinization that we've discussed in this chapter. The black smoker fields tend to occur along axial valleys or axial crests of active spreading centres, where newly formed oceanic crust is accumulating and driving a fluid circulation fueled by upwelling submarine volcanism. Contrast that with the hydrothermal carbonate with its serpentinization association. Such zones occur away from axial spreading centres. In the case of the Lost City hydrothermal field, we're located some 15 kilometres away from the spreading centre, atop an eroded piece of the mantle, which is 1.5 to 2 million years old. It's been uplifted and its overlying basaltic section has been stripped. It's still a fractured crust, and there the fluid circulation is being fueled by exothermic reactions associated with serpentinization. In terms of the vent exits, they tend to be quite focused in the black smoker fields with temperatures in excess of 300 degrees centigrade. Some can be as hot as 407 degrees centigrade. The white smoker zones tend to be somewhat cooler, temperatures in excess of 250, 270, up to 300 degrees centigrade. And then we can also get, surrounding those venting zones, a more diffuse system, still temperatures in excess of 100 degrees centigrade, where we have not focused vents but diffuse outflows associated with extensive microbial development. Contrast that with the hydrothermal carbonate scenario, where we tend to see far fewer focused distinct vent orifices. Where we do see them, the fluids exiting tend to be in the range of 40 to 91 degrees centigrade, so much cooler than in the smoke vents. We tend to see a system where we have broader diffuse venting outside of highly focused orifices. The fluids themselves are also quite distinct. In the black smoker fields, we see highly acidic, pH between 2 and 5, metal and sulfide rich escaping fluids with variable amounts of silica. They have no magnesium and no sulfate. They lost that on their downward descent in the circulation cell. In contrast, when we look at the venting fluid chemistries in our hydrothermal carbonate systems, the fluids venting are quite alkaline. pHs are between 9 and 11. They're quite poor in metals and silica, but they are highly enriched in calcium. They contain some magnesium and some sulfate, and hence we see the aragonite-calcite-brucite association. The volatiles, the dissolved volatiles in a smoker vent fluid tend to be dominated by volcanogenically derived CO2, helium and H2S. We can also get some H2 and methane, but hydrogen and methane aren't dominant. Whereas in the venting fluids of the hydrothermal carbonates, we tend to see fluids which are highly enriched in hydrogen, along with some significant levels of methane. So it's a very different set of fluid associations. We don't see the H2S, we don't see the high levels of CO2 that we see in the smokers. But we do see fluid-rock interactions ongoing, so that quite often the vent fluids also contain abiogenically formed, low molecular weight, short-chain hydrocarbons, the beginnings of life. In terms of the nature of the venting fluids, the hotter venting fluids in the black smoker fields can be quite extensive, and they tend to be quite particle-laden. This is where we tend to get extensive plumes of metalliferous particulates settling. Those plumes from the black smokers can rise as much as 200 metres into the overlying water column on the seafloor. Contrast with that, the hydrothermal carbonates, we tend to see relatively minor plumes. They're generally less than 50 metres in rise height, typically less than that, and they're quite clear. They tend to be particle-free. The black smoker fluids are quite metal-rich, which is what makes them so economically significant, and they include sulfide minerals such as chalcopyrite, pyrite, sphalerite, along with amorphous silica, and abundant ephemeral anhydrite. The anhydrite in a black smoker or white smoker association such as Tag Mound can make up 60% of the mound volume. But of course that then dissolves away as we have cooling, and that anhydrite goes back into solution to create breccias. But both the white smokers and the black smokers have extensive precipitation of hydrothermal anhydrite and extensive accumulations of the particulates coming out of those venting fluids. Whereas in the hydrothermal carbonates, the precipitative phases are quite simple. They are carbonate dominant with aragonite, calcite, and lesser brucite, with the calcite and the brucite tending to occur in the interior of the vent. So in areas of active venting, it's very likely that this carbonate, this aragonite, and also this calcite and brucite nucleates on what are filamentous bacterial strands. So we see travertine-like, biogenically formed microtextures in our hydrothermal carbonate associations. There are very different microbial associations when we compare the black smokers with the carbonate and hydrothermal fluids. We get dense, diverse colonies of eubacteria and archaea on a black smoker with significant colonies of chemosynthesis that can utilise a range of hydrogen sulfide, hydrogen and CO2, compared with the hydrothermal carbonates where we see very dense colonies, mats of eubacteria with very high diversity, along with the archaeal association dominated by a single group of methanogens that can produce and or oxidise methane and hydrogen. Sulfate reduction can be quite important, along with sulfate oxidation, in the cooler areas with quite high densities of eubacteria occurring in those areas. Living on that base of the food chain in the black smoker group, we get very dense and diverse, visually impressive colonies of large animals that include rifty of the tube worms, along with clams, shrimp and mussels, crabs and limpets, all utilising that chemosynthetic microbial community that forms the base of the food chain. The community in the biomass is less diverse, and with less biomass, they're less visually impressive. They tend to be much smaller organisms. Typically, the organisms living on the mats in a hydrothermal carbonate venting system are typically less than a centimetre in size. They're dominated by the grazers, the gastropods, along with some rare crabs and shrimp, but still with relatively high diversity. And some of that macrofauna is related to the mid-oceanic black smoker fauna. But in all, it's quite distinct. It's a system which has less impressive visually macrofauna, and it's dominated by gastropod. It's not as visually diverse as what we see on the black smoker ridge. Both of these systems, the black smoker field and the hydrothermal carbonate fields, are associated in the archaeal with possibilities for the origins of life. What makes the hydrothermal carbonate so interesting is that we form abiogenically short-chain hydrocarbons, which are the beginnings of life. It's been argued that these hydrothermal carbonate systems may be a better indication of what our life formed in the early Archean than the black smokers, but the debate continues. Certainly the hydrothermal carbonate systems have been used to argue that we could have life present extraterrestrially in the moons of Jupiter and Saturn.